get started as well. Similar to before, we'll talk a little bit about meshing. I've got it up here. We'll go through some of these slides. I've got some kind of suggestions, some tutorials, and some additional slides that you guys can kind of peruse through that I thought just might be interesting. When it comes to meshing, right, some of the things that we're really trying to do when it comes to goals of meshing, and we're trying to create a meshing strategy, is to create something that's accurate. Right, accuracy though comes down in the meshing aspect of it. Just thinking about mesh quality, right? Good mesh quality will ensure that we've got some good convergence in our actual simulations. We're thinking about efficiency as well. So thinking about maybe the element type that we're using. Where do we have refinement? Are we capturing the flow physics and the flow features that we're interested in? How kind of cheaply can we do it as well? If we can run things relatively quickly, it just means that we can run more design iterations, right? And then the other thing is generation as well. So ideally, if we're doing a lot of design iterations, we want to make sure we can do it pretty quickly, which is why using things like name selections is super important. Now, the goal is always to find kind of a compromise between all three of those aspects of it. We've got two platforms really for generating meshes. So I'm going to be talking to you about Fluent Meshing. We'll go through an example and go through the actual workflow. There are two aspects to Fluent Meshing. So I'm going to be going over what's called a watertight geometry workflow. That assumes that you've got a watertight geometry, so using things like the enclosure tool. If you've got STL, dirty geometry, maybe it's not quite created, we've got what's called this fault tolerant meshing, so it's not in beta anymore. We're not going to go through it, but I'll give you guys some access to where you can find some tutorials. There is also things like ANSYS meshing, so it's a little bit simpler, and we've got different techniques that we can use really to make sure we're picking up exactly what we expect. Right. I want to fire it up, and we'll kind of come back to some of these metrics. Right, that's something I'd like to do. Just to be simple, right? This is a previous geometry that I was playing around with. The enclosure is a lot smaller, right? So it's not exactly, I wouldn't take this and do a CFD analysis on it, but I'm using it just for the analysis that we're going to be looking at. There is a body of influence, but I'm just going to just hide it for this particular case, right? What I should have is some boundary conditions, so inlet, outlets, walls, symmetry, and a couple of things through there as well. And we'll bring it straight in. So if I've got, by the way, the geometry over here, I don't necessarily need a space claim thing if I've got a STL or whatever. I can bring it straight into Fluent. If I go to my start menu, just type in Fluent, you find Fluent 2020 R2. One of the key things is to make sure you've got everything saved in one directory. So I normally take that path and put it into my working directory over here. We can open up meshing with all these features. You can do it manually if you want. In Space Claim, again, it's just easier. Go over to here. There's a Fluent tab in the workbench. We'll open up with the watertight workflow. You can create your own and a bunch of other things there as well, but we'll open that up. You can see the working directory automatically gets populated with where the actual geometry is. We're going to be using double precision. So generally, if you're using turbulence, anything, it's double precision. I'd only really run in single if you're doing some troubleshooting and you need some quick results, right? When it comes to the machine, so we're going to be using 4 cores. Look, most computers, laptops will have 4 cores, right? When you go fire up Task Manager, you'll see you've got 4 physical cores. You don't really care about the logical processes. Those are hypothetical cores, which CFD doesn't really take that into account. I've got i7 7900, 3.1 gigs, 32 gigs of RAM. So the more mesh count that you have, the more RAM you actually need to run the simulation. So often you guys will find if you've got a 16 gig, machine, you're actually limited by how many elements you can actually run. I've got a P4000. We're not going to be using any GPU compute or anything like that for this particular example. It is something that is doable, right? But if you're going to use that, maybe have a bit of a chat with us. It's a little bit more complicated. It's not like you can just select it and it's good to go. There are a couple of things you guys just need to keep in the back of your mind before you get started, right? So you can also see, by the way, just having Space Claim open, We've got some other stuff going as well, taking around 12 gigs of RAM. So having something with a decent amount of RAM is pretty important. Let's fire this up. So again, that's all good. Here, so while we're here, learning resources. So there's some Answers learning resources if you want to go through them. You've got access to our stuff as well. If you go to the help again, you can access that help information, right? So we'll just hit the start button and we'll fire up Fluent. In the meantime, I'm just going to close some other stuff just to make sure I'm not trying to kill my computer. Okay, so cool. Everyone should be able to see that. So we'll try to stop, by the way, today around 12 o'clock-ish. I don't. No one likes sitting down for too long. We'll do what we can. All right. So Fluent Meshing. This is the Fluent Interface. We'll talk a little bit about this and then go into our actual workflow. All right. So top of the ribbon over here, depending on what we want to do, it might change. We've got some additional kind of controls up the top. Things like selection filters as well, so things like zoom to fit. We can play around with these things as well if you want to, by the way. You can move them, change them around. At the moment, we're in orthographic. So we can change it over to perspective. We can kind of play around with it, mess around with these things. The ruler can come in over here as well, a bunch of other things. At the bottom here, so if I show face edges, so this is the faceted geometry that comes in. I can do things like select my nodes, select specific facets, even things like, so you can see these are name selections, right? So that's the name selection. That's one for symmetry. I've got some additional tools in here. So if something does come to you and it's not exactly the way that you want it, you can actually do so. If you've got something selected, you can hide certain components in here, rename, isolate. You can even do things like remesh, separate them as well. So if you've got something that's tied together, you can actually separate them, then rename them, making your own name selection, things like that. All these things are doable inside Fluent. It's just, remember, one of the tenets of, I guess, getting a good mesh strategy is making it easy to use, right? Easy to generate. If you have to do this every single time you get a new geometry, it becomes a bit annoying, right? So having things like name selections come in cleanly from geometry, again, whether you're using SpaceClaim, whether you're using SolidWorks, whether you're using Inventor, Creo, whatever, I always recommend that, right? The console here, so the console, we can actually, it gives us a bit of information. I can actually, if I'm hitting enter, I can actually see a bit of it as well. So let's, so if I hit enter again, you can see I've got a bunch of different things here. If I select something, it's like a file structure, right? So if I go into file, there are a bunch of commands in here. So I can actually use what are called TUI commands to load things up as well. And I can create journals from that if I need to automate any of my process. I've got this workflow tab. So I'm going to be using the watertight workflow. It kind of spells out exactly what I need to do. If I can create my own things or actually play around with them. There's also the outline view. So this is a little bit more intense. Everything that that's been automated here, you can actually manually do it on the outline view if things start to go wrong. But generally, let's just stick with what we've got, and we can kind of take it from there. So there's quick search as well, by the way. If anything goes wrong, do a quick search for it and it can help you out. So geometry has been imported in, comes in as CAD, units are in millimeters. So everything you see here is in millimeters. We can take a next step. We can add things like local sizings. So if I create that, by the way, if I I select that, let's just hide a bunch of these things. You can see this is like the faceted geometry that's come in, right? So this is the CAD that's going to come in. We can add local sizings, right? Which is probably what I'm going to do around this region. So the different ways that we can add it depending on exactly what we might be interested in, right? So we can give a name, growth rate. There are different types of things that we can do. So face sizing, body of influence, curvature and proximity. Depending on what we're interested in, we can specify things like sizings. These labels are all labels that I created in SpaceClaim, right? So these are all my groups, my name selections. If you go over to the zone, right, you can see a bunch of them are still there. They're just, if you have things that aren't exactly easy, you'll just see a bunch of weird ones in there as well. So I generally recommend just stick with labels. What I might want to do for the first one is The general mesh, you know, because I've done this before, doesn't really refine around some of these features, right? So I want to do what's called a curvature sizing. So the curvature sizing is going to add more elements around some of these curved components, right? I want to focus on the front wing in this particular case. If I select the local sizing, the big box is the max sizing. The small boxes, let's just change this to something like 20. All right, so it's like a preview. Small boxes you can see are these ones over here, right? Now, what happens is that around here, I want a lot of elements across there. So maybe let's leave this as 1 for now, and we'll make some changes to that a little bit later on. We'll kind of play around with it, right? So I can do that. Let's give it a specific name as well. So I know exactly what I want. I can then start to add my local sizing, right? And maybe another thing that I might want to do is add some specific sizing around my wheel and my suspension. Again, maybe the same thing. Maybe I want to make this a bit coarser, right? I really don't need a lot of refinement around that region. If I make this say 2 mil, right? I know I've got some regions like around here. You know, maybe again, I might not need a huge amount of refinement around there. The other thing that I want to do is what's called proximity. So proximity will add, in this particular case, elements across this edge, right? Ideally, I want 2 to 3 elements to capture that edge really well. It gives me a lot of great quality around that region, so it allows me to, you know, capture what's happening, right? So if I'm not sure, I can, you know, let's just say I use my node selection. I can pick these 2 nodes out. I've got this measurement tool. It's a 5 mil. Okay, if I want to have at least 2 elements across there, I want my minimum sizing to be around 2 mil. You know, maximum around, you know, let's just say, let's give it a little bit larger than I need to, right? And I want to pick up the front wing, right? The problem with proximity is that it can overly refine everywhere, which is why we don't want to use it, you know, in every single component. It might overly refine around some of these regions, and if I'm not really interested in it, I'm just unnecessarily adding complexity to my design, into my mesh. So I've got a couple of things here. I can go back and revert and edit and start to play around with these things. This is the meshing for everything else in a way, right? So I haven't added anything around that chassis, right? So it's actually going to use my, you know, my global sizings to pick up what it might be doing around here. I'm not super interested in what's happening around there. That's fine. 200, let's just make it even because it's nice. I'm interested in, we'll just leave it as curvature for now. We'll leave this angle as default as well. And we'll go advanced options. If there's anything specific, I can, you know, look through some of these things as well. If I select the help, it'll tell me a little bit about what it is. And if I'm not sure, I can go to the actual online help. So let's generate that surface mesh. It'll give me a bit of information at the bottom, you know, what's actually happening as it's going through there. And within a couple of minutes, I'll have a surface mesh that I can have a look at. Generally with this stuff, right, like I was saying before, right, start coarse, you know, I generally start a coarse mesh with some geometry, get my boundary conditions acting what I expect, make sure that things are going in the right direction. And then if I'm happy, then I'll go back and actually start to add refinement. Everyone works a little bit differently, so I'm sure when you go about it, you'll figure your own kind of your way out. Right. The meshing techniques that kind of we use for some of that local sizing, there weren't too much, right? But there are a couple of additional things that you can start to do. So as an example, on the left-hand side, there's a face mesh of around 3 mil and there's a body sizing of around 3 mil. When we look at the actual geometry, we can see again the body sizing enforces that sizing internally, whereas the face sizing just occurs it over the face, right? That proximity, remember before, if I've got proximity between faces, it'll actually put 2 elements between these 2 faces. Sometimes that's what we want, maybe not necessarily. If we specify edges, again, it'll do exactly that same thing, right? Just put proximity between the edges. You can see these geometry features around here are really coarse. On the other side, you know, it's picked up quite a bit. Curvature again, so we're just picking up curvature. That normal curvature angle, so it just specifies, you know, at what angle should it put an element depending on the local sizing, right? The minimum sizing. If you want to put more elements across there, you can actually either reduce the minimum sizing or make this sizing a little bit smaller, right? This mesh should be created, so it tells you, if we just fire this up, blah, 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 a bit of information, some regions. So I've got this region, average skewness, right? What my face count is, so how many elements do I have, what do I have, and how long it took to actually generate the mesh, and what my quality is, which is really good. So if I wanted to, I can insert my clipping planes, right? I can start to move this around. This is just a surface mesh, so nothing is inside. And then you can go in and start to inspect some of these regions, right? So you can see here, this 1 mil, it's picking up kind of what's happening around here, right? So it's a bit coarse, you know, maybe I might want to go back and think about refining that. This has made it quite a bit finer, so it's trying to put faces across the edges as well. So if I take a note on that, that's probably going to be around, 2.5 mil. So maybe might want to go back, instead of faces, I want to put edges, right? And you can see as well, so afterwards, the chassis over here, relatively coarse, that's kind of what I expected. And if we go back here again, it's relatively coarse. It's not really picking up too much, but I'm not too worried about that at all. The sizing out here, you can see it's around 200-ish. You can, again, go in using a ruler. And generally, this is what I'll do afterwards. Really inspect what's happening. Is it what you expected? What if you zoom in all the way in here? Right, okay, it's got roughly what I wanted. Let's just say we made a mistake, which we did. Let's go back to our proximity, revert and edit. You can see here again, it's very fine across here. Not what I want. I don't need that much refinement around these regions. Let's just flip it over just to edges, hit update, and we'll hit update on that one as well. We've also got, so bodies of influence, so we talked about that as well. If we've got a face label, pick on that. If we have a control type, which is called the body of influence, we can specify something. When you look at your surface mesh, that body will actually disappear because it uses that region just in the volume mesh for refinement, right? So you can see the effect at the bottom and what happens over there. So this is where, if we wanted to use refinement, we could kind of play around with that. For this particular case, let's just keep it relatively simple. So you can see here as well, again, so my mesh count has decreased. So we've got 150,000 elements just on the surface. Before, if we go up a little bit, right, I think we had around 200,000. So we've saved, 50,000 elements, which is good. It'll help us a little bit later on. And again, zooming in, right, edges, great. Not much around there. Brilliant. That's what I wanted. Right. Cool. All right. So let's go through the rest of the steps. So we need to describe the geometry. We've got fluids. We don't have any fluid boundary conditions. We've just got one component. We don't need shared topology. Update boundaries, right? So the chassis is a wall, front wing. The ground is a wall as well. We've got inlets over here, suspension, symmetry, everything. If you've got the correct names, by the way, these things will just kind of automatically populate themselves, right? We've only got one region, which is fine. Now, adding boundary layers, right? So in this particular case, what I might want to do, so I'm going to leave it a smooth transition for now. Actually, what I might do, normally what I actually play around with is last ratio. I'll leave it smooth right now. Let's just have 3 layers, leave it defaults. I want it to grow in the fluids. I want to select the zones though, right? So let's select the labels instead. And I want it to grow on my chassis, my front wing. I'm going to turn this highlighting off. The ground, my suspension, and my wheel as well, right? So we'll try to put elements all the way across there. So we'll have a look at that. And when it comes to generating my volume mesh, right, I've actually got a couple of different methods that I can generate it with. So TETS, Hex, Poly Hex Core. I'm going to use a Poly Hex Core, and we'll just hit the generate button. We'll let that generate in the background. While that's going, so let's just go back to a couple of our slides. So the reason I'm using Poly Hex Core, there are some differences between some of those elements, right? The Poly Hex Core is a new meshing technique from ANSYS. It allows us to create polyhedral elements on the actual surface and then hex elements on the far field. It's also parallelized, so if you've got more cores, it actually takes a lot less time to generate a mesh. This is an example of a test case that I created actually on my laptop, just to show the difference when it comes to efficiency. So I've got a couple of different mesh types: Poly Hex Core, Poly Hex Core, and TET. The poly ones just have a poly surface finish. The tet ones have a tet surface finish, right? The Hex Core, you can see, actually has a hex refinement region internally, and you can see, I've got both of them on the poly side of things. I've got two refinement regions, so one around here, another one around here. On the poly and the hex side of tet side of things, I don't have that, right? I've got refinement, but they're not hexes. Generally, we use, these unstructured tet grids because it's really good at actually picking up geometry and curvature and complicated geometry, especially. If we've got just geometry, sometimes some people might make it, a fully hex grid. Hex is generally more efficient, but it can be very time consuming when it comes to actually generating a proper mesh. So, I've found personally for these types of external cases, a poly hex core is a really good middle point there, right? This is an example that I did on my actual computer. So if you're not sure, always just make a small test case, right, and go through it. So for the exact same sizing, what you saw before, when it comes to the elements, so the poly hex core actually created considerably less elements compared to the other different mesh types. When it comes to actually running the simulation, so I think it was taking up to around 200 iterations to converge, you can see the poly hex core again took a lot less time compared to some of the other ones. And when it comes to resources as well, you also got to think about RAM. So you can see here, my 7 million tet grid took around 25 gigs of RAM, whereas my 1.3 mil poly grid took around 8.6 gigs of RAM. So when you guys think about the different mesh types, there are different problems associated with them as well that we'll talk about. But also think about how much resources do you have, how much RAM do you have, how much CPU time, how long is it going to take for you to actually generate something? Do you have access to a cluster maybe? That might be interesting as well. When it comes to efficiency, the things to keep in mind though is that with the hex core, there are these hex jumps, and if you don't kind of take a good look at them, if they're around the areas of interest, they can cause some problems. The other problems with polyhedrals that you just got to keep in the back of your mind is that because of the size of it, right? If you've got a lot of curvature, you might need some more elements to pick it up, right? So you can see here around this region, if you've got a large jump, you might be missing information. So making sure, around here, you've got additional refinement is very important. Sometimes what can happen is that you've got this, large cell jump size. There are some new things like this avoid 1 to 8 feature, which you can put poly elements across there, and that can help out quite a bit. The other thing sometimes with your polyhedral elements is that if you've got elements that are too large, you can see this splitting. So we'll try to split the actual poly element to maintain good quality if you've got very fine boundary layers, right? So that might be, there are some things that have been improved, but you might need to make your poly mesh maybe a little bit more refined compared to a tech grid. So these are things when it comes to your particular use case, you might want to do a little bit of testing, right? There's no one size fits all solution. When it comes to hex, again, the other benefit of hex grids is that if you've got flow going in a specific direction, it can be very efficient. Whereas sometimes with tech grids or polyhedral grids, you can get numerical diffusions, right? If the alignment of the grid is in line with the direction of the flow. What starts to happen though is that when you've got flow that's going not exactly in that alignment, you can get what's called numerical diffusion, and generally it doesn't really matter what type of element there. It really comes down to how much sizing you've got. When it comes to the boundary layer aspect of it as well, so we were using smooth transition. I generally use the last ratio. You can specify what the first cell height is and the ratio from like the last couple of elements. It allows you to really control the first cell height to get a good Y+, and you get a nice smooth transition from the boundary layer to the actual far field as well. So before we continue, I'm sure this grid's probably created. Awesome. So let's just use my clipping planes here. So if I can bring this over here, I can draw my cell layer, right? So you can see I've got, actually, if we get rid of this for now, you can see I've got, some poly elements around there. They're nice, they're picking up the curvature around these regions. A couple through here as well, what I expect. I've got some additional refinement around some of these regions, which is what I wanted. And I've also got, it's relatively coarse around the chassis, which is fine. I've got my boundary layers being created as well. And if I show the actual cell, if I zoom in, you can see I've got boundary layers coming all the way around, right? Same around the wing. Right. So if you can see in this particular case, though, I don't really have refinement around some of these regions. Kind of it's a little bit refined, but not exactly what I wanted. And if I don't have any of these mesh controls, my boundary layer starts to grow quite a bit. Maybe it's far enough away that I don't really care too much, but this is why maybe you might want to go in and start to add refinement. You see some of these jumps as well. Again, you're going from a small to a big jump pretty quickly. We can really start to fix that up as well. Again, the key is we don't want any of this stuff around any areas of interest for us. So if we go back, I can choose different ones if I want to. What I want to do actually is increase things like my buffer layer by 1 and my peel layer. And I just want to show you guys, if I select this avoid 1 to 8 octree transition, see what it looks like. The buffer and the peel layer, I'll show you guys what that is a little bit later on. So while that's generating, what I want to talk a little bit about, though, is accuracy. So this is an example about a mesh study that I did for an external error case, right? Accuracy, it's one of those things. There's no easy way to figure out if the mesh that you've got is appropriate. You have to do what's called a mesh independent study. In this particular example, we're looking at, let's just say, the vortex coming off kind of the front wing. I've got 2 refinement zones, so I've got something that's really fine around this region over here and something that's really coarse around this region, right? Looking at the flow structures, though, you can see the one at the top is refined. You've got this vortex that's actually shedding from that end plate and traveling all the way down past the wheel. At the bottom, because my mesh is really coarse, I've got some dissipation, numerical dissipation, and you can see it's not really traveling all that far, right? So I'm actually not picking up a lot of the fine flow features because my mesh isn't appropriate. Another way to look at it, again, taking another section, you can see around that vortex, I've got multiple elements around the thickness of the vortex, understanding exactly what the vorticity is, what the velocity is doing around that region. The bottom here, again, not a lot, so it's really not showing me too much. Again, there's no one way of going about it, right? There's you really want to be looking at what your interest area is. So maybe in this particular case, it's downforce, right? And you progressively want to be making some of these things smaller. And then what you'll start to find is that after a while, those results will start to kind of, flatten out. And that'll let you understand that you've got a mesh that's kind of independent of the actual results, right? So if you make this mesh finer and finer, your drag value isn't going to get more and more accurate. Sometimes, though, they can be pretty difficult depending on the flow structures that you've got. In things like the FSAE stuff, you've got finer and finer flow structures that you start to pick up. And then your computational resources start to become a bit of a problem. So you really got to think about what do you actually have available to you. This is an example of that car. So let me just get, let's go back into this. So we're looking at the front and we're taking a section through everything. I'll run it a couple of times to show you guys. The top is the I think it's the coarse mesh. The bottom is the finer mesh from memory. Sorry, no, top is the fine mesh, bottom is the coarse mesh. All right, so let's just run it. We're looking at vorticity coming off the car. You can see these are the vortices being produced from the actual car. So this has a front wing and a diffuser, right? You can see at the very end, what the different mesh looks like. One of the things I do want to pick up, though, and talk about is things like, the vortice coming off the front here. So if we play that, we can see the vortice comes off. In the top here, we've got kind of these 2 well-defined vortices. Over here, you can see we've only got a couple of elements across there. And what happens is that after a little bit, we can see with this finer grid, we've got these smaller flow features that don't really get picked up in my coarse grid, right? If I take another section through here, again, I can see these fine flow features coming off all the wings and things like that. At the bottom, it's just kind of one big clump. And again, kind of going through closer, you can see again more flow features coming off the wing. So again, refining the mesh more and more will pick up some of these finer flow features. It really comes down to, are these features important to what I expect or what I want? Do I need them? If I add more mesh, it means that my simulation is going to take a lot more time to actually resolve as well. So it's a bit of a trade-off. Cool. So if we look at, this is going. almost done. So that took a lot longer. So again, you can see 400-bit minutes, we're around 2 million elements. If we scroll up a little bit, what do we have here? 100-bit minute, we had under 1 million elements, right? So some of those changes have changed how many elements I've got, right? So if I can take my cut edge, just kind of bring it along. If we look at the mesh, what we'll start to see here is instead of those, big transitions, we've got a bunch of poly elements that have been put through there as well. And then the other thing is that we've actually got more of these kind of smaller ridges before it transitions out. And that was, why I played around with the buffer and the peel layers as well. All right. So next thing I want to talk a little bit about is quality. So we weren't really doing too much in this particular case because the quality comes out pretty well. But generally, if something does start to go wrong, we can insert these like custom tasks. So we can say improve the volume mesh. Let's just make this say 0.15. Let's just leave it at that. And we can hit improve. We'll just let it kind of do itself in the background. Generally though, so this is an example, sometimes you need to go through and actually make some changes to your geometry, right? In Fluent, we look at what's called the orthogonal quality for these polyhedral elements, right? This is an example where I needed to go back and actually make some changes. Generally, again, red's bad, blue's good. So if I've got something that comes to a sharp end and I've got these small inflation elements, sometimes I can get bad quality elements around there. So you might need to go back and actually make some changes to your geometry. It'll come with a little bit of experience to understand what changes are appropriate and what things that you might actually need to do. And again, if you're not sure, just do a little bit of testing, right? Make 1 or 2 of them, do a little bit of comparison between them. You can see that having just one element across there isn't appropriate. So you might need to add maybe 3 or 4 elements to get a really good high quality mesh around some of those regions. Generally for some of these FSAE meshes, you can have multiple sizings, multiple bodies of influence, curvature and proximity depending on what component. You can see here I've got a pretty coarse mesh outside here, pretty refined around this region. Zooming in, I've got some additional refinement boxes that I might be interested in. I've got proximity around here. You can see I've actually got a bit of splitting around my front wing. It tells me maybe I need to go back and make some changes. Again, you can see I've got a bit of proximity, some curvature around some of these places as well. I'm picking up some nice curvature around there. A couple of key points. So identifying, what mesh type might be good to use, what software is good to use, and also, what are your actual goals, right? What resources do you have? Do you need to do a bit of a study or a bit of a comparison between some of these things? Identifying things like what's important for your actual simulation. So in this particular case, maybe it's the boundary layer resolution, right? That might be important because you want to pick up things like the pressure gradient, which will indicate what the forces on the actual wings might be. If you pick them up incorrectly, you might be misrepresenting separation, which can then cause you problems, right? Because it's going to change the vortices that come off there. So having a clean mesh is also generally going to help with convergence. Couple of things you want to keep in mind. So things like orthogonal quality, 3 elements. I'll let you guys go over some of the finer points. 3 elements across, some of these small features to keep quality really good. Checking and double checking things like areas of importance, high curvature, influence, and using bodies of influence to really pick it up. If you're not sure about how fine your mesh is, again, build a small matrix for yourself and do some testing. So maybe you've just got one parameter here, the body of influence around the near domain. You're progressively making that smaller and smaller, and you're just looking at successively how the actual mesh is changing. If you go into your tutorials, so again, the getting started stuff, you've got the tutorials to go through, so 6 to 8. There is also the fault tolerant workflow. So the fault tolerant, instead of requiring nice clean geometry, you can actually do what's called wrapping. So you can wrap internal or even external geometry as well. You can also have a look at that. Additional slides, maybe I'll. So there's some things about states. What I wanted to show real quick though, the growth rate and surface quality. Okay. I've got to slide onto the buffering those peel words. I'll start to add that and add it to you guys later on. You can see here, so it started to improve the actual mesh quality, which is what it's wanted. If something starts to go wrong, it'll actually tell you, this has gone wrong. It'll indicate where the problem is, right? So the other really cool thing that you can do is save it out. So you can save out this workflow file, right, with all the features in it, right? You can, call this one course or something like that. And you can then open it back up later on. So if you want to actually give your meshing workflow, your meshing strategy to someone else, they can do that. The really good thing as well is that all of these meshing, these local sizings is just based off of your name selections. So if you make a geometry change, as long as your name selections are exactly the same, it will pick up the exact same name selection. Right. Even if it doesn't, the good thing is that you can put into here curvature wing. Let's just say it's changed to, the name has changed to something else. You can clearly tell, all right, this is the curvature that this guy's added for this wing. Maybe something's gone wrong. I can go back and manually change it. If you hit the open button and you go number 3, so let's just say this is a new file. Let's fire this up. You can see when it loads it up, all the different things that you've done are inside there. It even remembers where the original import geometry was, right? You can go through that process. You can actually hit the one at the very bottom, and it'll progressively go through each of these steps. We can save something out, so we can write out a mesh file or a case file, or we can actually hit the switch to solution button, and it'll automatically switch it over to the Fluent solver. This is also, by the way, where you've got that fault tolerant workflow. So some different options will start to pop up, right? So these are things like you need to specify whether it's an external or an internal geometry. You can actually create geometry in this region in things like refinement regions. If you've got things like leakage, right, you can actually specify that, setting up boundary conditions, and then creating a model, and then switching it over to the solution as well. I think those are the main things that I wanted to go over for meshing. So the next ones are going to be all about things like turbulence, which Errol's actually going to do next time. So actually a bit earlier, do you guys have any questions at all? Again, just chuck it in the chat or raise your hand. Pretty good so far. Cool. So in the meantime, if I'd definitely go through and go through the actual tutorials to kind of wrap your head around what's happening and exactly what you can do and what you can play around with. A couple of things I'll show you guys as well. So if you go to our Learning Hub, log in, Fluids, well, for instance, actually, if we just go to the FSAE stuff, there are some more kind of content, some tutorials in here as well. So if you do things like 2D wings, bunch of other presentations as well if you guys are interested. We've also got things on like the rocket competition as well as like the UAV competition. The online trainings that we've done previously are all here as well. If you want to check out the highlights, you can go through that as well. These, I think there are the other tutorials, by the way. So if you go to pre-processing, Fluent Meshing, the top here are all the watertight workflow tutorials, and underneath there are what's called the fault tolerant workflows. And these are the training materials for that. And then underneath that, there are some additional videos as well that you guys can really go through. Again, different physics depending on what you guys are interested in. Cool. And again, so these are the modules here. So going from 1 to 4 is all geometry, 6 to 8 is meshing. And you guys will go through some of the additional ones later on and some videos that you can have a look through as well. Cool. Any other questions at all? If not, we're actually finishing it relatively early. Does anyone have a project that they wanted to go through at all or talk about?